Find the area of the region bounded by y equals 8 minus x, the x-axis, and y equals square root of x plus 4. So to solve this, we need to sketch the graphs of the given equations. And it would be helpful if we know the intersection between each pair of equations. So we begin with the intersection between y equals 8 minus x and y equals square root of x plus 4. So we equate 8 minus x and square root of x plus 4. Then we square both sides of the equation, giving us 8 minus x quantity squared on the left side and then x plus 4 on the right side. And then we expand the expression on the left side, so we get x squared minus 16x plus 64, and then transpose the expression on the right side to the left side, so we get minus x minus 4 equals 0. So simplifying, this gives us x squared minus 17x plus 60 equals 0. And then we factor this, giving us x minus 12 times x minus 5. And we equate each factor to 0, giving us x equals 12 and x equals 5. Now, we need to find the y-coordinate corresponding to this x-coordinates that we obtained. And we must check whether we will be getting the same result if we substitute the value of x to y equals 8 minus x and y equals square root of x plus 4. So when we use x equals 12, notice that there are two different values of y that we will be getting. So when we substitute 12 on y equals 8 minus x, we will be getting negative 4. And when we substitute 12 to x on y equals square root of x plus 4, we will be getting positive 4. So we got two different values of y, which means this is not a point of intersection. So we are now going to use x equals 5. And when we substitute 5 to the x of y equals 8 minus x, and the same thing with y equals square root of x plus 4, we will be getting the same value of 3. Therefore, our point of intersection, this is a valid point of intersection, and it is represented by the ordered pair 5, 3. So we will not be considering anymore x equals 12 because we got two different values of y. Next, we find the intersection. We will be finding the intersection between the x-axis and y equals 8 minus x. Note that for the x-axis, the equation is y equals 0. So we simply substitute 0 to y on y equals 8 minus x. And this gives us x is equal to 8. Therefore, y equals 8 minus x will be intersecting the x-axis at the point 8, 0. And then for the intersection between the x-axis and y equals square root of x plus 4, again, the x-axis is just y equals 0. So we substitute that on our second equation. We get 0 is equal to square root of x plus 4. And then squaring both sides, we get 0 is equal to x plus 4. And x is therefore equal to negative 4. So y equals square root of x plus 4 will be intersecting the x-axis at the point negative 4, 0. Okay, so next we will be plotting these points and sketch our curves. So we plot the point 8, 0. So this is the point 8, 0. And then we also have the point negative 4, 0. And the point 5, 3. So let us begin by sketching y equals 8 minus x. So y equals 8 minus x will be passing through the points 5, 3 and 8, 0. So this is y equals 8 minus x. And then y equals square root of x plus 4 will be passing through negative 4, 0, and 5, 3. And since one of our boundaries is the x-axis, so the described region will be as follows. Okay, so now we are ready to find the area of our bounded region. So in this solution, I am going to present two different methods. One using a horizontal element and the other using a vertical element. And let us observe which of the two is easier to apply. So I will begin with a horizontal element. So using a horizontal element or a strip. So the formula will be a is equal to the integral of x right minus x left dy from C to D. So C is the lowest y-coordinate of the region and D is the highest y-coordinate of the region. So let us illustrate this by drawing or sketching a horizontal element inside our region. So suppose we draw our horizontal element this way. Observe that whether we put this horizontal element at the bottom part or at the higher part of our region, the right side of our element will always be touching y equals 8 minus x. At the same time, the left side will only be touching the equation y equals, or the graph of the equation y equals square root of x plus 4. So we can now set up our integral to evaluate the area. So A will be equal to, so the lowest y-coordinate of the region is 0. And the highest y-coordinate of the region is 3, coming from the point 5, 3. Now, we set up our equation by identifying what x right is. So this will be our equation on the right side, y equals 8 minus x, but we need to get the expression of x in terms of y because we're supposed to write it as xr. So solving this gives us, so y equals 8 minus x, we find that x is equal to 8 minus y. So this is our x right. Minus, for x left, we have y equals square root of x plus 4. Again, we need to get the expression of x in terms of y. So to do this, we square both sides of our equation. So we get y squared is equal to x plus 4. And so y squared minus 4 is equal to x. Therefore, our x left is y squared minus 4 dy. So simplifying first, then integrating. So we get negative y squared minus y, and then we have 8 minus negative 4, or simply plus 12. And then the integral will be negative y cubed over 3 minus y squared over 2 plus 12y evaluated from 0 to 3. So when you evaluate this, we get the area of 45 over 2 square units. So this is the area of our bounded region. Now, I mentioned that we are going to try using an alternative solution. So this time, we're going to use a vertical element. And we know that for this technique, we are going to use the formula y up minus y down dx. And then our limits of integration will be a and b, where A is the leftmost x-coordinate of the region and B is the rightmost x-coordinate of the region. Now, let us sketch a vertical element inside our region. So, if this is our vertical element, we observe that y up will be y equals square root of x plus 4. And y down will simply be the x-axis, which is again y equals 0. However, if we draw our vertical element somewhere on the right side of our region, we find that our y up is no longer y equals square root of x plus 4. Instead, it is y equals 8 minus x. This is an indication that we are supposed to divide our region into parts. Okay, so the division will be where the change happens. So at the point 5,3, we project it downwards. That will be the division of our region. So let us label the first one as A1 and then the second as A2. So we set up the equation for A1. Again, the reason why we're dividing our region into parts is because y up is not consistent throughout the region from left to right. So we need to set up two equations where y up is y equals square root of x plus 4 on one region or sub-region, and then y equals 8 minus x on the other sub-region. So for A1, so y up will be square root of x plus 4 and y down is 0. So we don't write that anymore. We just put in dx, and our limits of integration will be negative 4 to 5. So negative 4 because the leftmost x coordinate of our region is negative 4, and the rightmost x coordinate of the region is 5. So this will be from negative 4 to 5. So if we integrate this, we need to use substitution rule, and doing that will give us this solution: x plus 4 raised to 3 halves over 3 halves, or simply 2/3 when we take the reciprocal, evaluated from negative 4 to 5. So when we solve this, we will find that A1 is 18 square units. Now, we need to get A2 as well, and this time the region would have the leftmost x-coordinate as 5 and the rightmost x-coordinate is 8. So the region ends at the point 8, 0. So therefore, our upper limit is 8. Now, y up will be 8 minus x, while y down is again the x-axis, whose equation is just 0. So we just have 8 minus x dx. Integral is 8x minus x squared over 2, evaluated from 5 to 8. Again, solving this one gives us 9 over 2 square units. Now, the total area will just be the sum of A1 and A2. So we add 18, that is the area of the first subregion, and then A2 is 9 over 2, the area of the second subregion, which when we combine, we get 36 plus 9 over 2, which gives us a total area of 45 over 2. It's the same result that we got when we used a horizontal element. Now, this means that we can actually solve for the area using either a horizontal element or a vertical element, and we will be getting the same answer. However, we observe that using the horizontal element is easier compared to using a vertical element because we have to subdivide the region into two parts using the vertical element. So this means that you can choose whichever technique you want to apply, horizontal or vertical. You just have to check which one is an easier method to apply.